Children, let us continue the chapter electricity. Now about the heating effect of electric current. What is heating effect of electric current? You go through some examples. Electric fan becomes warm. Mixer grinder becomes warm if they used continuously for longer time. Here you are using the electric current to run the fan, to run the mixer and to run the grinder. The electrical energy is converted into mechanical energy. But here some part of the electrical energy is converted into heat. So the electric fan, mixer, grinder becomes warm if they used continuously for longer time. So you can observe that electric current produces heat. Electric current produces heat. You know that battery or a cell is a source of electrical energy. When the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. The chemical reaction within the cell generates the potential difference between the two terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. To maintain the current, the source has to keep expending its energy. To maintain the current, the source has to keep expending its energy. Where does this energy go? A part of the source energy in maintaining the current may be consumed into useful work like rotating the blades of an electric fan, rotating the mixer, grinder, etc. Rotating the motor of the mixer, grinder, etc. means the electrical energy is converted into mechanical energy here. Rest of the source energy may be expended in heat to raise the temperature of the gadget. We often observe this in our everyday life. That is, an electric fan becomes warm if used continuously for longer time, and mixer, grinder becomes warm if they use it continuously for longer time. On the other hand, if the electric circuit is purely resistive, that is a configuration of resistors only connected to a battery, the source of energy continuously gets dissipated entirely in the form of heat. As the resistivity of the conducting wire increases, the amount of heat producing also increases, because more the resistance, more will be the opposition to the flow of electrons through the conductor. As the opposition is more, means the vibration of the particles of the conductor will be more and the kinetic energy of the particles also increases. So the conducting wire or conductors or any object becomes hot, through which the electric current passes through it. So here, if you use the object with more resistivity, if you are using purely resistive circuit, that is a circuit which consists of only some resistors connected to a battery. Here, if the circuit is having resistivity, maximum resistivity, then you can have the maximum amount of heat produced in the resistors, maximum amount of heat produced in the circuit. The energy of the battery which is connected in the circuit gets dissipated entirely in the form of heat produced in the resistors. So, the phenomenon of production of heat in a resistor by the flow of an electric current through it is called heating effect of current or Joule heating. So what is heating effect of electric current. Heating effect of electric current is a heating effect of electric current is a phenomenon of production of heat in a resistor by the flow of an electric current through it. So, what is heating effect of electric current? Heating effect of electric current is a phenomenon of production of heat in a resistor. By the flow of electric current through it. But here, why you have taken the resistor? The production of heat depends upon the resistivity of the conductor. So simply you can say that what is heating effect of current? When an electric current is passed through a conductor, heat is produced in it. This is known as heating effect of current. When an electric current is passed through a conductor, you know that electric current will always flow through the conductor. If the conductivity is more, means more amount of electric current will pass through it and less amount of heat will produce in it. Therefore, here as the resistivity is more amount of heat will be produced and the heating effect will be more. We know that as the conductivity increases, the resistivity decreases and heating effect also decreases. Therefore, here let us consider a purely resistive electric circuit. Now let us consider a purely resistive electric circuit, means which offers maximum resistance. Here it is a resistors of resistance R. This is a resistor of resistance R, and the potential difference across its end. Here let us consider X and Y are the ends, and the potential difference across X and Y, potential difference across the ends of the resistor is V. So here the resistance of the resistor is R, that is resistance of a resistor. You take resistance of resistor is R, and potential difference across it, potential difference across it means here between X and Y is V, and T is the time during which a charge flows across the resistor. Here that is nothing but the amount of current flowing through it. So here we have taken, let Q is the amount of charge flowing through it and T is the time taken. T be the, or you take time taken, or justly you take it as time. Time is T, and amount of charge flowing through it. Charge across the conductor. Charge across the conductor is Q, and work done in moving the charge Q through the potential difference V is VQ here. So work done in bringing a charge Q across the potential difference V, that is across the ends of the resistor, the potential difference is considered V. Therefore, the work done in bringing a charge Q is VQ. Then you know that the source must supply energy equal to VQ in time. The source must supply energy equal to VQ. That E is also equals to what? VQ, because energy supplied is equals to work done. Therefore, here as work done is VQ, the energy supplied is also VQ, and the power input to the circuit by the source P is equals to, you know that, V into Q by T. P is equals to V into Q by T, that equals VI. That is equals to VI. So you got that P is equals to VI. And also you know that energy supplied to the circuit by the source in time t is E is equals to P into T. Here you know this one, E is equals to V into Q, because here energy supplied must be equals to the work done. And also one more relation you can have, that energy supplied to the circuit by the source in time t is, therefore you can have the relation here E is equals to P is VI. P is VI, so you will get V into I into T. The energy supplied becomes V into I into T. Here you take T is the time, I is the current, and V is the potential difference across the resistor. And what happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. So this energy is converted as a heat in the circuit. Thus, for a steady current I, the amount of heat produced in time is H is equals to V into I into T. Here the energy is converted as a heat. Therefore, you can have the relation H is equals to V into I into T, where V is the potential difference, I is the current flowing through the circuit, and T is the time. T is the time in which the energy is supplied to the circuit. According to Ohm's law, you can have V is equals to IR. V is equals to IR. Put the value of V, that is IR, in this relation. So write H is equals to V is I into R into I into T. Then you can have H is equals to I into I is I square R into T. So this relation you got, and this is called H equals I square RT is called Joule's law of heating. This is called Joule's law of heating. So you write that is H is equals to I square RT is called H is equals to I square RT is called Joule's law of heating. Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance R, and directly proportional to resistance for a given current and also directly proportional to the time for which the current flows through the resistor. So what is the statement of the Joule's law of heating? Statement of Joule's law of heating. Joule's law of heating says that heat produced in a resistor is first one directly proportional to the square of current for a given resistance. Square of current for a given resistance. And directly proportional to resistance for a given current. And directly proportional to the time for which the current flows through the resistor. Directly proportional to the time for which the current flows through the resistor. Then what is the statement of Joule's law of heating? Symbolically it is H is equals to I square RT, and heat produced in a resistor is directly proportional to the square of the current for a given resistance, that is I square. Next, second one, directly proportional to the resistance for a given current, this is, and directly proportional to the time for which the current flows through the resistor. That is I square RT. You are taking directly proportional to the square of the current, directly proportional to the resistance of a resistor, and directly proportional to the time for which the current flows. This is the statement of the Joule's law of heating. In practical situations, when an electric appliance is connected to a known voltage source, the equation H is equals to I square RT, equation H is equals to I square RT is used after calculating the current through it using the relation I is equals to V by R. Here, if the potential difference is known, here when the electric appliance is connected to a known voltage source and H equals I square RT is used after calculating the current through it. And how will you calculate the current? By using the relation I is equals to V by R. Here V will be known and also R is of known resistance, R is also known. Then I can be calculated by using the relation V by R. After, you can use the relation H equals I square RT. After, you can calculate heat produced by using the relation H is equals to I square RT. Now about the practical applications of heating effect of electric current. The generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful electrical energy into heat. You know that there is a loss of energy in the form of heat if it is not necessary. In electric circuits, the unavoidable heating can increase the temperature of the components and alter their properties, and also sometimes they may damage the appliances. However, heating effect of electric current has many useful applications. You know that iron box, electric toaster, electric oven, electric kettle, electric heater, and many familiar devices are works on the basis of Joule's heating. So, the main use of heating effect of electric current is household heating appliances. Household heating appliances. Which are the household heating appliances? Most of the electrical appliances used in daily life are based on heating effect of current, such as room heater. So you can use the room heater to get the rise in temperature, and electric toaster, electric toaster, electric iron box, electric iron box, electric iron, electric oven that you can use at home, electric oven, electric kettle, electric kettle, geyser, etc. The heating element used in these appliances should have high melting point and high resistivity. Why they must have high resistivity? To produce more amount of heat. Why they must have high melting point? Because due to the large amount of heat, they must not melt. So here the heating filament used in the heating appliances must have high melting point and high resistivity. The second important application of Joule heating effect is incandescent electric bulb. The electric heating is also used to produce light as in an electric bulb, which is called incandescent electric bulb. Here the filament must retain as much of the heat generated as is possible. It consists of a filament of a fine metallic wire enclosed in a glass bulb filled with chemically inactive gases like nitrogen, argon, etc. Nitrogen, argon, etc. The filament material should have high resistivity and high melting point. Therefore, tungsten with a melting point 3380 degree is used for bulb filament. Tungsten is a filament having high resistance and high melting point. Therefore, in incandescent bulb, tungsten is used as a filament, heating filament. When a current is passed through the filament, it gets heated to a high temperature and emits light. Why nitrogen or argon are used in the incandescent bulb? The filament should be thermally isolated as much as possible using insulating support. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of filament if it is isolated thermally. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. In incandescent electric bulb, large amount of energy is converted into heat and small amount of energy is converted as a light. Means naturally there is a loss of energy in the form of heat. In incandescent bulb, there is a loss of electrical energy in the form of heat, even though it gives the light by using the heating effect of the electric current. Another important application of Joule heating is the fuse, which is used in electric circuits. So what is fuse? It is a safety device used to protect electrical appliances from strong currents. It protects circuits and appliances by stopping the flow of any unduly high electric current. A fuse wire must have high resistivity and low melting point. It must have high resistivity and low melting point. It is usually made from an alloy of tin and lead. It is made from an alloy, and that alloy is having the combination of tin and lead. You know what is alloy? It is a homogeneous mixture of metal with metals or metals with non-metals, and the fuse wire is made by alloy of tin and lead. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1 amps, 2 amps, 3 amps, 5 amps, 10 amps, etc. For an electric iron which consumes 1 kilowatt electric power when operated at 220 volts, a current of 1000 by 220 amps, that is 4.54 amps, will flow in the circuit. In this case, a 5 amps fuse must be used. Fuse wire is put in series with the live wire of the circuit. The electric installations are thus saved from getting damaged, because here that when the current exceeds the safety limit, the fuse wire melts and breaks the circuit and prevents the damage of the electrical appliances in the house. In this way, here electric fuse is a protective device. Now about the electric power. So what is power? Power is the rate of doing work. So what is power? Power is the rate of doing work. And also in other words, it is the rate of consumption of energy. Rate of consumption of energy. You know that energy is the capacity to do the work and power is the consumption of energy or rate of doing work. Now the equation H is equals to I square RT. H is equals to I square RT gives the rate at which electric energy is dissipated or consumed in an electric circuit. In an electric circuit, how much energy is consumed is given by the relation H equals I square RT. This is also termed as electric power. When a current I flows through a circuit for a time t at a constant potential difference V, then the work done is given by the relation W is equals to VIT. Here, when a current I flows through a circuit for a time t at a constant potential difference V, the work done is W is equals to VIT. Therefore, you can have electric power P equals W by T. Electric power is W by T, as power is a rate of doing work. Power is a rate of doing work. Therefore, P you can have P is equals to W by T. W is VIT by T. So, you will get VI. And you got that P equals V into I. P is equals to V into I. And you know that V is equals to IR. V is equals to IR. So, in the place of V you can write here P is equals to IR into I. That is according to Ohm's law, V is equals to IR. And if you substitute the value V is here IR, then you will get P is equals to I square R. P is equals to I square R. And also you can have one more relation. Here you know that P is equals to VI and V is equals to I into R. Therefore, I equals, you can have V by R. I equals V by R. So, it becomes P equals V into, in the place of I, you write V by R. So, that becomes V by R. So, then you will get P equals V into V square by R. Here one relation you got that P equals I square by I square R, and the other relation P equals V square by R. Therefore, for P you can have three relation. P equals V into I, P equals I square R, and also P equals V square by R. These are the three relations that you can have for P. And how will you write the definition for the electric power? Now you take what is electric power. Take what is electric power. You know what is power? Power is the rate of doing work and it is the rate of consumption of energy. Now, what is electric power? The electric power of an appliance is the rate at which it consumes electric energy, or it is the rate at which work is done in maintaining an electric current in an electric circuit. And here the definition says that the electric power of an appliance is the rate at which it consumes electric energy. What is that electric energy or electrical energy? Electric energy is the total work done in maintaining an electric current in an electric circuit for a given time. So you write the definition for the electric power. What is the definition? You write the electric power of an appliance. The electric power of an appliance is the rate at which it consumes electric energy. It consumes electric energy, or in other words you can say that, or electric power is the work done. It is the rate at which work done is the rate at which work done in maintaining an electric current in maintaining an electric current in an electric circuit, in an electric. So what is electric power? The electric power can be defined in two ways. The electric power of an appliance is the rate at which it consumes electric energy, or the second one definition you can have here, electric power is the rate at which work done in maintaining an electric current in an electric circuit. Then what is the SI unit of electric power? SI unit of electric power is watt. SI unit of electric power is watt and its symbol is W. The symbol of watt is W, capital W. And what is watt? It is the power consumed by a device that carries 1 amps of current when operated at a potential difference of 1 volt. So what is 1 watt? You take watt is the, or 1 watt is the, 1 watt is the power consumed by a device consumed by a device that carries 1 amps of current, 1 ampere of current when operated at a potential difference of potential difference of 1 volt. Therefore, you can write 1 watt equals 1 volt into 1 ampere. That is 1 VA. 1 W equals 1 VA. The unit watt is very small. Therefore, for actual practice, we use a much larger unit called kilowatt. So, we are using kilowatt is the general unit, and you know that 1 kilowatt equals 1000 watts. 1000 watts. Since electrical energy is the product of power and time, that is here E equals, you know that E equals P into T. E equals P into T. Electrical energy is the product of power and time. The unit of electrical energy is watt hour. Here power is watt and time is hour. So what is the unit of electric energy? That is power watt. So you can have here unit of electric energy. Energy is power watt. You write power watt, that is WA. Power watt. WH. Then 1 watt hour. 1 watt hour is the energy consumed when 1 watt of power is used for 1 hour. So 1 watt hour equals what? 1 watt of energy consumed one watt of power used for 1 hour. Now the commercial unit is different here. The commercial unit of electric energy is kilowatt hour. That is kWh. kWh. Here it is WH, watt hour, and kilowatt hour. That is the, you may heard the word units of electric current. That is how much unit is there in the electric bill. So that is unit in nothing but kilowatt hour. 1 unit means 1 kilowatt hour. So let us calculate how much joule it is, how much watt hour it is. 1 unit of current. 1 unit of current. Generally kilowatt hour is termed as unit. 1 kilowatt hour means 1 unit of current. That is 1 unit of current means 1 kilowatt hour. And 1 kilowatt hour is 1000 watts. 1000 watts into hour means you convert it into seconds. That is 60 into 60 seconds. Then you will get 6 6 36 and 1 2 3 4 5 zeros you put. That is watt seconds. Here you can write watt second. Then that equals, here you know that equals 3.6 into 10 to the power of 1, 2, 3, 4, 5 and 1 point you have taken, that is 10 to the power of 6 watt second. 6 watt seconds, that equals 3.6 into 10 to the power of 6 joules. 6 joules. Joule is the unit of energy and this is the electrical energy, so you can convert this as joules. So what is the SI unit of electric power? That is watt. What is 1 watt? 1 watt is the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. So you can have 1 watt equals 1 volt into 1 ampere, that is 1 volt into ampere. Then the larger unit of the electric power is kilowatt. 1 kilowatt equals 1000 watts. And you know that electrical energy or energy is equals to power into time, P into time. So the unit of electric energy is watt hour. 1 watt hour equals 1 watt of power used for 1 hour. And the larger unit is kilowatt hour. You may heard the word, that is unit. So 1 unit of current equals 1 kilowatt hour, that equals 1000 watts into 60 into 60, you will get 36 lakhs watt second, that is 3.6 into 10 to the power of 6 watt second, that equals 3.6 into 10 to the power of 6 joule. So 1 unit of current equals what? 3.6 into 10 to the power of 6 joules. That is the commercial unit of current is equals to 3.6 into 10 to the power of 6 joules. Now that chapter is completed here.